Lesson 22, gravitational field strength. All right, so first off, we need to talk about what we mean by a field. And just to give you a bit of an idea of that. So what Newton, when they were trying to figure out what gravity is really, what what they wanted to know was, okay, let's say this is the moon over here and we've got the earth over here. And the question was, how does the moon even know that the Earth is there, or how does the Earth know that the moon is there? Like, what's connecting those things? Well, what was proposed is that there's these things called fields. So if I look at the field that is going toward Earth, this field would be going inward in all directions toward the Earth. And then they said, okay, well, if anything gets caught in that field, like the moon, then the moon is going to fall toward the Earth. So this is just a different way of thinking about something that we probably already kind of knew, right? And these are called field lines that I've drawn around the Earth here. And just for a little housekeeping here, if you were to have something that had a stronger field strength, you would just add more arrows. That's kind of the way they like to draw that. And this is going to become really important, and especially in Physics 30, because then we'll not only are we going to talk about gravitational field strengths, we're going to talk about electric field strengths and magnetic field strengths, and they're all kind of thought about the same, like similar ways. But yeah, so that's what we mean by field is like that something. If it's caught in its field, that means it's gonna be pulled in when we're talking about gravity. Okay, so talking about gravitational field strength, we're talking about just what strength is the gravity that's actually pulling this thing in. Well, we've already been kind of talking about this, but we've been referring to it up until now as acceleration due to gravity. So remember that 9.81 meters per second squared? Really, for simplicity's sake, this is our gravitational field strength. So nothing really new. The only thing we are going to do, though, is we are going to, instead of saying 9.81 meters per second squared, we're going to say 9.81 newtons per kilogram. And if you break down those units into what they actually are, they're the same thing. I'll show you actually. If I broke down the newton and what a newton is, so 9.81, and then instead of newtons, I'm going to write what a newton is. A newton is a kilogram times meters per second squared, right? Mass times acceleration. And so that's what a newton is, over kilograms. Well, kilograms cancel with kilograms, so the units are actually the exact same. So why would we change it up, you might ask? It's just a different way of thinking about it. So 9.81, it's saying that for every kilogram, there's 1 newton of force acting on it. So this is like just an easier way of picturing what we mean by gravitational field strength, right? We can talk about how many newtons per kilogram are being forced towards the Earth at that point. Same thing though. Don't get too caught up between the difference between the two. Yeah. So just a little bit about how we can come up with a formula to figure out what gravitational field strength is. Because remember, this isn't gravitational field strength. That's force. When we talk about gravitational field strength, we are talking about that G, or which is an acceleration. So gravitational field strength, acceleration, now the force. All right, so if we start out with the universal law of gravitation, the one that we were doing last lesson, right? And we compare it to one that we've been using more often, that Fg is equal to mg, or mass times acceleration due to gravity, same thing. And we just make those two equal to each other. So Fg is equal to Fg. So I'm going to say mass times acceleration due to gravity, and then big G, m1, m2 over r squared. Knowing that m here, that stands for like the mass of, the person. So we've got two masses here, right? We got the mass of the Earth, and we got, like, maybe let's say the mass of a person standing there, right? This would be m1, this would be m2. So the mass of the person would be this mass in that case, and that would be, let's say this mass in that case, m2. So they're going to be the same thing, right? That's the lighter mass. So you can see now that if we just divide both sides of the equation by m, that cancels with that, and we end up with, that cancels with that. We end up with just a is equal to big G m1 over r squared. And just know when you use this equation, because this is on your formula sheet as well too, right? This stands for the mass of like the Earth or the Sun or whatever we're talking about that is causing this gravitational field. So that might be, yeah, any kind of big object. So make sure you get that clear, because you'll have two options for masses, right? You need to know which one to put into your equation. Okay, and this is going to be useful for figuring out the gravitational field strength on any different planet, right? Because this should be the same on Earth, right? 9.81, but if you're on the moon, that would be different. If you were on Venus, that would be different. So take a look through example 1 and just make sure you can use the formula like it's showing there. Example 2, we've done ones kind of like this, right? So it says, what is gravitational field strength at a distance of 1.914 times 10 to the 7 above the surface of the Earth? That's a key word there, right? Because we don't care about surface of the Earth. We need from center to center. So we need the radius of the Earth involved too. If a person weighs 400 newtons on the surface, what would he weigh at this distance? So to figure that out, we got to go, radius is going to be radius of the Earth plus their altitude. So you find this from your data sheet. And then this one from the question, and the radius is that. And then really just plugging in and knowing that this needs to be the mass of Venus. No, Venus. No, what was this one? Sorry. Earth. Sorry, no, this one's Earth. I was getting this confused with the last question. So that'd be the mass of the Earth in that case. And yeah, just plugging in and you get the gravitational field strength of this. And your units could also be meters per second squared. So the next part is saying figure out their mass. Well, that's just using Newton's second law. F is equal to ma. And we know that acceleration due to gravity is going to be 9.81. And you might ask yourself, how come we're not using this number, right, that we just found for our acceleration? Remember, that was like way up in the sky, right? The reason is because it says if a person weighs 400 newtons on the surface. So on the surface, that's 9.81, right? So we have to use that number. The person's new weight can be calculated using, so then, yeah, we just use their same mass because the mass doesn't change, right? The mass is like how much stuff you're made of. It doesn't matter how high you go up into the atmosphere or away from Earth, it's going to be the same all the time, right? And your acceleration due to gravity, or your gravitational field strength, and then just plug it in. All right, just to be clear though, because this is a common thing that people make a mistake on, is they confuse the concept of gravitational field strength. This is really more equal to acceleration, right? Acceleration due to gravity, not F. It's not equal to F. Yeah, gravitational force and gravitational field strength are different. So if you look at these like three objects that we have here, right? This one, and this one. They all are going to have different forces of gravity, right? Because if you go, you know, F is equal to ma, or F is equal to big G m1 m2 over r squared. You should get the same thing if you do either of those formulas. You're going to get a certain force, right? That's going to be smaller for the small mass and bigger for the bigger masses. So all your forces are different. Your force of gravity is different for each one. Your gravitational field strength, which is acceleration due to gravity, is going to be 9.81 for all of them if you're on Earth. Okay, I'll pick up with the practice problems in the next video.